Welcome to our Solutions for NanoAnalysis podcast, brought to you by Bruker NanoAnalytics. We look forward to bringing you a new podcast regularly. My name is Cody Morton. I'm a marketing communications specialist at Bruker NanoAnalytics and an information enthusiast. If you like to learn from specialists in their field and hear what technologies are solving their problems, you will enjoy this podcast. Every session, we will focus on a different problem that our colleagues face in the lab and in the field. Some of the solutions will be a variation of ideas you may have heard before or even worked with. We will bring you these topics in a new and interesting way and introduce you to updated and thought-provoking results. We will talk about how the problem was dealt with in the past and what we're doing to solve the problem now and perhaps even envision future solutions. Join us as we talk solutions with a variety of scientists and technicians in many different industries in the Solutions for NanoAnalysis podcast. Energy has been around since the dawn of time. The first source of energy was the sun, as it provided heat and light during the day. People rose and slept with the light, relied on wood and dung burning for heat, and water power to generate basic mills. The Industrial Revolution kick-started our use of human-generated electricity. Most people credit Benjamin Franklin with discovering electricity in 1752, which he did by realizing that the sparks emitted from lightning strikes could generate power. The concept of the atom has existed for many centuries, but we only recently began to understand the enormous power contained in the tiny mass. In the years just before and during World War II, nuclear research focused mainly on the development of defense weapons. Later, scientists concentrated on peaceful applications of nuclear technology. An important use of nuclear energy is the generation of electricity. After years of research, scientists have successfully applied nuclear technology to many other scientific, medical, and industrial purposes. Nuclear research has benefited mankind in many ways, but today the nuclear industry faces huge, very complex issues. How can we minimize the risk? What do we do with the waste? The future will depend on advanced engineering, scientific research, and the involvement of an enlightened citizenry. Join us today as we talk energy. And Doug, let's have you go ahead and introduce yourself and introduce our guest.
Okay, so I'm Douglas Stauffer. I am the Senior Manager of Applications for Bruker's Hysitron product lines. I do work related to the Hysitron products or nanomechanical test instruments.
Doug, who have you brought with us today to talk about their problems and solutions?
Yeah, so today our guest is Dr. Peter Hosemann. He's a professor at the UC Berkeley School of Nuclear Engineering and also the department chair.
Hi, Doug. Thanks for having me. It's great to be here today.
How did you get interested in science, Peter?
Into science?
In science, yeah. What drew you to science?
Oh, well, how did I get interested in science? Originally, I guess I started off as apprentice as a farrier, horseshoeing, I guess. And later on, became a mechanical engineer, interested in mechanical engineering. And one thing I learned in mechanical engineering is that any design you envision is limited by the materials you have available to realize those designs, right? So you can, on the computer today, design the most interesting engine or rockets or what have you. If you don't have the right materials to make that work, then your design is going to stay where you put it, which is on paper or on a hard drive. They'll never see the light of day. So in order to realize engineering designs that are worth pursuing and pushing the envelope, you have to have the materials at hand, or at least understand the materials to make it work. And so that drove me really to material science at the end.
So is that what you did your doctorate work in?
Yeah. So then I started a master's and a PhD and a doctoral in material science at Montana Universität Leoben in Austria. The reason I went to the school is because it's the only school that offered material science at the time within the country. So the choice was easy. even though that Leoben is of course in the countryside and not in a big city. But it turned out to be very fortuitous because it's a small school, maybe comparable to Colorado School of Mines or similar, that's known in the US, which really, there's a lot of direct interaction between students and faculty, and first semester students can get easily engaged in research. One of the first things was I learned about atomic force microscopy in a class and approached one of the faculty, Professor Teichert at the time. And next thing you know, 2 months later, I was sitting on a DI3 doing atomic force microscopy on semiconductors, self-structured semiconductors as a first-year undergrad student, really. That only can happen at small settings, really.
Yeah, really hands-on.
And then I did actually my master's in organic materials on cellulose fibers, so man-made cellulose. The question at hand was, how is man-made cellulose any different from naturally grown cellulose, such as cotton? In other words, what's the difference between synthetic cotton or cellulose and the natural grown one? That was fascinating, of course, because very different from what metals and steels, but fascinating topic by itself.
So you made your way over to the US for your postdoc.
No, as a student.
Oh.
So I came as a summer student, really, in 2003, I believe. And somehow never left and still a summer student. So one thing the university asks to do is that you have to do, your summer is not yours, you have to do internship which is specific to what you study. It's a requirement. And that forces you to go and do internships, and happens so that I got in touch through an internship with somebody from Los Alamos National Laboratory. In fact, at the previous internship in Switzerland. And they invited me over to become an intern at Los Alamos. And that internship transferred into a PhD thesis later. And so I did the PhD research at Los Alamos while being enrolled at the school in Austria.
Yeah, so Alamos is definitely known for its energy research. So we can talk about energy, but what are the other big problems that science needs to tackle right now? I mean, besides energy, which we'll come back to.
Yeah, well, there's of course this whole field of biological sciences. In the middle of the pandemic, you of course want to say something about medical research. And there's a lot to be said for this. That there's a lot of problems which really can improve human lives by addressing various diseases, even outside of COVID, and just enhance people's quality of life. And there's a lot of things. And in materials, of course, that can lead to medical implants and other type of research in that sense, even outside of virology and things like that. That can have a big impact. As society grows older, naturally, people have to get help with overcoming daily challenges. And
materials wear, right?
Exactly, yeah. So
materials are just, internal or external. So
that's right. And we are made out of materials, right? So there's a lot of studies to do. And there's a big challenges with an aging society. Of course, energy we mentioned, we come back to that. And there's, of course, a lot of challenges and opportunities in information technology, right? In materials, I would argue that we're probably not as far along as other fields. And with treating data and learning from data out there, and even learning from historical data. And that's only the beginning right now. And there's a lot more work which we can and should be doing to benefit our work from this wealth of information.
Yeah, it's still a discipline, for the most part. It's you make something and then you test it. So
right.
Yeah. So let's focus in on this energy. And so you're the head of the Department of Nuclear Engineering, obviously interested in producing energy. And tell us a little bit about, why nuclear, even versus other forms of energy.
Yeah, I mean, Austria, of course, doesn't have any nuclear power, and it's not thing you can study there. But I was introduced to nuclear energy then in Switzerland and then later in Los Alamos. And what fascinated me about nuclear energy is, first of all, it produces very little greenhouse gas emissions. In normal operation, none, right? Of course, the production produces some in mining, what have you. But overall, it's very minor impact. But it's also pretty interesting that it's really one of the energy forms which is probably the only one which is truly man-made, right? So in all other energy forms, you're harvesting wind, solar, or burn coal or something like that, something that Earth gives you. In nuclear by itself, that's not something that would necessarily happen, maybe with one exception. And two exceptions, I guess the sun is the other one.
Yeah.
But it's something we create as humans as an energy source. And that is fascinating that we put this technology on the table. And of course, it has tremendous energy density, right? So there's nothing like it with the same amount of energy density. You a relatively small footprint plant can create tremendous amount of energy. That's why we put them on boats, for example, right? Because they don't need much space and produce a lot of energy to drive boats through the ocean and all that. And of course, with the enhancement of greenhouse gas emission concerns, and global warming, which we feel every day in California and many other parts of the world, of course, it is a very viable way to create electric and other types of energy to help maintain our standard of living.
Absolutely.
And not emit greenhouse gases. It's not either or. It's not nuclear or solar. It's all of the above.
Yeah.
Right? All of it. And with electric mobility more coming to play and such, that's even more important than ever, right? And population is growing, so you need to come up with that. We also see that process technology is more and more relying on electricity and other forms of energy. For example, steel plants are starting to look into, can you make steel with hydrogen instead of carbon, which is great, but then they have to make the hydrogen, which again requires electricity. So at that point, you again asking the question, where does that power come from? And it's all of the above. What is interesting is there's a lot of synergies at times between all the different energy forms, right? So you have high temperatures. You may find high temperatures in nuclear reactors, but you find high temperatures, materials exposed to high temperatures in solar concentrator power just as well. And being in materials, then you really can make an impact in all of the energy technology, not just one.
Yeah. I mean, we could look at something really simple like a Carnot cycle, right? And just talk about efficiency, making efficient things. So what do you need for efficiency? You need high operating temperatures and low output temperatures. And so high temperature materials, I mean, it really plays the gamut. I mean, if you were to do something like an internal combustion engine, the most efficient is the highest operating temperature. So,
right.
Specifically, can you talk a little bit about your research and how that fits into solving some of the still existing problems that moving forward nuclear?
Yeah, our research is centered around materials in extreme environments. And of course, nuclear environments being one of the most extreme ones one can envision, right? You have high temperature, you have radiation, you have impact of ions and plasmas, if you talk fusion, you have corrosion, you have all of it, all at the same time, all the same place taking place to the material. And you want it, reliably over 60 years or a longer lifespan of this power plant, right? And it was always fascinating to me in a way is that if you think of what, our nuclear power plants are meant to operate now 60 years. What a 60-year lifespan of any engineering structure, right? We have hardly any bridges or other structures which are that old. So this is a really long time. And they need to operate reliably over this long periods of time. And so we really have to understand the materials we deploy in these extreme environments. Conventional materials, something simple like carbon steel or stainless steel, naturally. And we want to be able to predict how long can they be in service without, being at major risk of failure or become unusable. Or we also want to see new materials which may allow us to go to higher temperatures, which may be more reliable, which allow us to reduce cost in construction, any of the above. So you really have to go back then to the material science behind all this to find out what knobs can you turn on to enhance the properties you're interested in, right? And so materials in extreme environments, again, nuclear environments being one of the most extreme ones and maybe the most challenging one, due to the additional degree of freedom of radiation damage and fission products and transplantation products you would not necessarily have in a solar power plant or other circumstances. But the rest of it is applicable. So if it works in nuclear, it's likely that it's going to work in other things too, right?
Developing new materials, and you talked about a number of the challenges. From my very limited experience, one of the challenges is then even handling the materials. You've done some sort of test, right? You've exposed it, right? You can't just like put it in your pocket and take it home. So
yeah, I wouldn't advise that. But yeah, of course, if you, you can. Let's take operational plants, right? So in currently operating plants, you have to continuously over the 60-year lifespan or longer ensure that the material still fulfills the requirements. How are you going to do that? You test the material that's in the reactor or the reactor is made out of. Now, you have to prove to yourself and to the regulatory agencies that your material is still going to last a worst case scenario, for example, a loss of cooling accident or something like that. And so you got to ensure that the properties are what you think they are. Now, in order to do that, you have to take out the material, as I said, either a surveillance sample, that is material that's in the core, seeing higher dose than the reactor pressure vessel itself. So you see a little bit ahead of time what's going to hit you maybe in a few years down the road. It's not too dissimilar from what aircraft industry is doing at times. And so you examine that. Now, of course, these materials, when they come out of the reactor, they're highly radioactive, or they are even parts of the reactor, and they're sort of biopsy, if you will. Yeah. But they're highly radioactive, and you have to handle them behind thick lead walls and concrete shielding at times, and lead glass, and with robotic arms and all that, which is expensive and time-consuming and not necessarily easy to do. Now, what we set off to do is to reduce the volume of the radioactive material dramatically so that you do not have to handle large quantities of that material. And if you reduce that a lot, then naturally the amount of radioactive material you have to handle scales with that too, to the point where even spent fuel can be handled by a person, outside of a hot cell lead shielding, if it's small enough. And then the question is, what's the smallest volume you can still get properties from that are meaningful and tell you something about the performance of that part? How many cubic micrometers of materials do you need to assess a yield strength, for example?
Yep.
Or a hardness number, or whatever the properties you're after. And that brings us then to like small scale mechanical properties, naturally, because we want to assess this on the smallest possible volume. And that brings us to small scale mechanical testing, be it, non-indentation, be it micro compression testing, microtension testing, micro cantilever testing, shear testing, whatever people can envision, really, right? And simply driven by the fact that we do not want to handle large quantities of radioactive material. That's one aspect. The other aspect is, of course, as in any engineering structures, we have more valuable components than others. So a weld, for example, is much more susceptible to a failure or a heat affected zone in a weld than bulk rolled material. So we would like to know what's the weakest link. And I would like to know what's the property of the heat affected zone in contrast to what's the property of the sheet metal or other components. And by that, you also reside to small-scale mechanical testing because you can probe specific regions of interest and can probe the weakest link and therefore say, well, my overall reactor may be fine, but there's a specific weld I have concerns about, and I would like to know more about that specific weld in order to make a lifetime assessment. So that's also an important aspect to be able to probe local regions of interest.
Yeah, I mean, even in outside of the nuclear field, right? It's you have a medical device and you have welded A to B, and if you do a tensile test, you know that the B is always going to fail because it's a ductile metal, right? But really, when you look at device failures, it's that weld that fails.
And of course, there's then a third aspect to this in research, maybe more research centered, right? In order to get to a decent dose on a material, it takes years to get that in a reactor, right? So in most advanced fast reactors, you get maybe we measure dose in a unit called DPA, displacement per atoms, which is a strange unit a little bit, but so in a fast reactor, high end, what have you may get as much as 20 to 25 displacements per atom in any given year. Okay, but you would like to know how this material performs after 200 dPa, right? Let's say. So you need many years until you get to that dose level. And so a PhD thesis, lasts 5 years and not 10. So a student would like to finish their question on hand, within a reasonable time frame. So, but the solution to this is, or one way out of it is that you accelerate your dose irradiations, and that acceleration can happen through ion beam accelerators, where instead of putting the material in a reactor, you put it in an accelerator. And that accelerator bombards the material with heavy ions rather than neutrons or other particles. That allows you to go to much higher doses in a shorter period of time and be able to answer your more fundamental questions, what is the defect structure going to look like, and so on and so forth. The challenge with that, however, is that ion beams have a limited penetration depth into materials. So depending on what ions you're shooting at what target, but you're typically talking no more than 20 to 30 micrometers penetration depth. So that means you have only 20 to 30 micrometers of material available for whatever your examination is going to be. And in this instance, we're obviously interested in mechanical properties. Again, that brings you to small scale mechanical testing, be it indentation-based testing, pillar testing, tensile, what have you, to get a meaningful property. And so then the question you're trying to answer is, how do you compare ion beam dose to neutron dose, for example? And you can compare some aspects, maybe not all, but the majority anyway. And can you then say something about the long-term performance of a component by irradiating with ions rather than neutrons? And then you're comparing small-scale mechanical test data from ions to small-scale mechanical test data from neutrons, for example, and try to learn something from that.
So, Peter, for the listeners who may not be familiar, can you describe what displacement per atom means?
Yeah. So it's a way we assess dose, right? And dose, by its definition, is the effect of radiation on matter. Right. And if you're a biologist, you typically use gray or so, right? An organic person, that tells you how much energy is absorbed by a given volume of material. If you are a materials scientist and deal mostly with hard materials like metals, that is not a particularly useful dose. We're trying to assess, again, the effect of radiation on matter. Now, the effect of radiation on matter is based on the fact that you're displacing the atoms within a matrix crystal from the original lattice site. And that's leading to physical changes. Now, the dose we use in this instance is displacement per atom. So one displacement per atom means that every single atom in this material was displaced one time from the original lattice site. Which is, of course, when you think of a reactor, which fast reactor may see 200 displacements per atom, that every single atom in this component was displaced 200 times, statistically speaking, anyhow, from their original lattice, which is a tremendous amount, right?
Yeah, that's pretty crazy.
Yeah, it's pretty crazy. So why does this not crumble to dust and we deal with single atom powder at the end of the day, right? Well, fortunately, those 200 displacement per atoms don't all happen within one instance. They happen over long periods of time. And there's, of course, diffusion taking place in between. And the atoms can find back a lot of lattice sites as there. But you leave damage behind. And so one thing to note is that the dose unit is not the only important parameter in this equation. The second important parameter, equally important to dose, is temperature. Because 100 200 displacement per atoms at 0 Kelvin means that your atoms stay displaced.
Yes, yeah. They don't relax back into their favorable condition.
Exactly. Yeah. 200 dPa at 0.9 times the melting point of the material means they're all going to jump back to lighter side and it's not going to do anything, right?
Yeah.
Or the extreme example would be 200 dPa in a liquid means nothing because there's no lighter side. So, but we're dealing with the meso time and temperature scale in between, if you will, where interesting things happen. And so depending what your operation temperature is, in addition to those, that tells you how much of the damage is actually going to last within the material. So then the other thing, maybe dPa is, since we use this as a unit, but it's maybe one of the very few units you cannot measure. There is no measurement tool you put in there and say it like a meter, right? And a meter roll out and it's like, okay, that's a meter. But dPa, it's a calculated unit based on a model we use, and that's typically a Kinchin-Pease model or a variation of it to assess this dose unit.
So you haven't like tagged each individual atom and then tracked it.
We're not doing that.
So back to the small scale mechanical testing, you really, I think, outlined very nicely here why it's important. Go into a little bit about your lab, what your preferred small scale mechanical testing methods are, why. And I know you use the Bruker equipment, so I don't know if you want to say a few things about that as well.
Sure. Well, as everybody here probably listens, and you're obviously familiar, is there's a wealth of small-scale mechanical testing tools. But what you're trying to do always is trying to find the right tool for the right question. And so indentation, for example, is a very good tool. And, the TI-950 in particular is a very nice tool for large mappings, for, lots of data in a relatively short amount of time. But it can be sometimes challenging to interpret that. What is hardness, right? What does hardness mean outside of the resistance of a material against penetration of another object? It's very hard to relate hardness to, an engineering property. We engineer materials with yield strength and strain numbers and UTS and fracture toughness, not with hardness, unless you're a hard film coating person. So while it's very useful to get large numbers of data quickly, it's really, we use the hardness a little bit more, many times much more as a qualitative assessment. We then have empirical equations to relate towards maybe quantitative design number. But hardness by itself is interesting, but not something we use to design a reactor with directly. Yeah. But it provides the statistics, right?
Absolutely.
That's a huge advantage of it, right?
Yeah, going back to that weld example, if you look at something very simple like the Tabor relationship, right? Hardness is 3 times your yield strength. It's really defined by this constraint factor, but in a weld, that constraint factor changes depending on the material. If you have intermetallics don't have a constraint factor. So hardness it's a little bit more abstract than, say, the yield strength, right? With yield strength, the ASTM guidelines are very clear on how calculated. So
exactly. And one thing everybody I think who does small scale mechanical testing but now starts to appreciate is that maybe coming from mechanical engineering was not clear to me early on as a student that these properties are really not absolute properties, right? We learned over the years that scaling effects. So we learned over the years that we have to really compare the same thing to the same thing. As you pointed out, right, intermetallics have different properties than regular metals, maybe. And so these relationships may not hold be true through all of this, which is really a different way of thinking about it. Because if you're a mechanical engineer, a meter is a meter is a meter. It doesn't really matter where you are. But if you a materials person, you learn that stress for this material on that length scale is not the same number on a different length scale. Now, how do you design some component with that knowledge is a challenge, right?
Yeah. I noticed that you're very interested in micromechanics and not necessarily going that down that one more length scale to the nanomechanics, your sample sizes has 0 free dislocations, then your yield strength is nucleation dislocations. Or if you have existing dislocations, then they run to the surface. And then again, you're back to nucleating dislocations rather than moving them. So that's very different than how a bulk metal deforms.
Right. Well, yeah, that's right. And so the question I tried to ask always is, what is my strength determining feature in a bulk material, right? What is that? And then try to design the length scale of the mechanical test around that feature. If my material main strength is determined by small precipitates, nanoscale precipitate, I can probably make my test a lot smaller and still get valuable information from engineering application. If my strength determining feature is grain size, let's say, then I have to design my small scale test much larger, or have to account for the fact that I'm always going to do single crystal experiments in some way, and do much more simulation later on. So it's important to realize what is the feature you're trying to sample and design your experiment around that. Now, earlier we only talked about hardness, right? So the other property, of course, you asked that question, was my favorite mechanical test method in a way. Again, the feature is, there's pillar testing, right? Pillar testing is giving you yield stress. It doesn't tell you a whole lot about plasticity, maybe, but it does give you yield stress, much more direct than a hardness test would do. And if it's in situ, that's why we like in situ, we actually learn how it fails. I think that's a huge plus we get from in situ versus ex situ, is that not just the yield strength number, that what is ex situ test will give me that too, but I also see how it fails. Is it sudden? Is it like one band? Is it a particular grain boundary it happened to fail on? All these information I will get from the in situ one. I cannot easily get ex situ the same way. And but it doesn't tell me a lot about strain, right? So it doesn't tell me
what ductility you have. Absolutely.
Yeah, right. And if I want that information, which I would argue has not been widely studied, not in the small scale testing world anyway, then you would have to do tensile tests, right? Microtensile, or maybe shear or other kinds. Then you get total elongation and things like that from. And you have to, again, be careful, how does a small scale total elongation or uniform elongation relate to a large scale? And you have two powers at play. You have the material's intrinsic microstructure and materials performance, but geometry matters a lot too, right? So anybody who has done any mechanical engineering knows that there makes a tremendous difference if you have a lot of surface versus a lot of volume. And that's why STM standards define these ratios. So you cannot necessarily directly go from total elongation of microscale to macroscale property, but those laws exist, and you can try to refine them and make educated comments about that. So for each property you want to sample, there is a test you can do, but you have to obviously know what property you want to sample and why, and what's your strength determining or sometimes even strain determining feature you want to design your test around that.
Thanks, Peter. Getting to the specific tool, you have a Hysitron Pi88. Can you go into some of the things that you find very useful about this tool, or strengths you find for this tool?
Yeah. I mean, it's very versatile, right? We use it a lot, as you know. And we use it for indentation, pillars, tensiles, cantilevers, for all of it. And it's a great tool. We have the heated options, so we can do heating, which is really something I think in energy technology, which is very, very needed. Of course, we always want more temperature and higher sensitivity and better controls and so on and so forth. But obviously, there are challenges with that. We also have a Pi85 actually, which is modified to do cryo, and so you can cool as well, which can be of interest, particularly for space applications and what have you.
Absolutely.
And so that versatility. We can do heating and cooling is super helpful. It is very user friendly. That's important at the university, right? So that cannot be overstated. The importance of user friendliness. at the end, we also educate a large number of students, and we cannot, nobody can always build the equipment from scratch and learn how everything works. You have to basically be able to train somebody quickly and make sure that they get good data in a short period of time. And that is very helpful in the Bruker equipment, for sure. So versatility, the load range is quite convenient now. The 88 particular has much higher load range. The heating and cooling options, the ease of use, those are all features we really appreciate.
Thank you for your time, Peter, and thank you to our listeners. I learned something today, and so that's always a good thing.
Thank you to our speakers today. If you would like more information about today's topic or to submit a topic idea, please email info.bna@bruker.com. You can also check out more information in today's show notes. Join us next time as we look at a new solution with more scientists and technicians in all sorts of industries.